Can a Commodore 8-bit machine like the C64, the C128 or the VIC-20 encode QR codes? I'm pretty sure they can. The question is, how long does it take and how much memory is needed? In this video, we will look at how these machines perform in Commodore BASIC, in C and in 6502 assembly language. In addition, we'll compare these to the Mega65 and the X16. Just so you understand what the challenge really is, I'll explain what's needed to generate the QR code real quick, and I'll focus on the interesting parts only, and some of the steps definitely are. QR codes basically consist of dots, light and dark ones, and as anyone can guess, these represent the smallest unit in computing, bits. In the context of QR codes, these bits are called modules. The minimum size is 21 by 21 modules, and this is called version 1. Version 2 is 25 by 25 modules, so each version increments by 4 modules. The maximum version is 40. Feel free to do the math. Okay, I implemented a QR code generator in Commodore BASIC 7. This is a multi-step process, and I simplified things a bit to make things faster. My goal is to allow plain text like URLs to be encoded into QR codes. This could be used by games to provide links to game manuals or the website or whatever. Now for the first step, as you all know, Commodore computers don't encode text as ASCII characters. So we'll need to convert the user input from PASCII into ASCII. The algorithm is easy. We just need to check whether a character is inside a certain range and change its value accordingly if it is. We support version 5 codes maximum. This allows for 108 bytes of encoded data. And for this, Commodore BASIC takes only about 1 second, no big deal. QR codes have error correction capabilities. The standard supports 4 different levels, but we'll restrict ourselves to the lowest level for the sake of simplicity. Next step would be to identify which type of data we are about to encode. Multiple types are supported depending on which characters should be encoded. For any URL, the byte type is a safe bet. This is Nayuki.io, by the way. This website provided great insights into how QR codes work. If you're interested, you should definitely check this out. I'll post a link in the description below. Besides the interactive step-by-step explanation and the generator itself, Nayuki.io also provides QR code generator libraries for all common languages. And all of that made it much easier for me to understand how all this works. So a big thank you to the maintainers. This video is not in any way sponsored by Nayuki. This is just a big shout out. The step of identifying the most appropriate mode is easy for us. We'll always pick byte mode. Next step is to prepare the data so it can be aligned accordingly inside the matrix that makes the QR code. All the data needs to be continuously written to bytes so they can be processed by the next step accordingly. In the comments of my source codes, I described this as the data stream. The data stream starts with specifying the data type we just talked about. The byte type is described by module values 0, 1, 0, 0. So the data stream starts with 4 bits. That's half a byte so far. After that comes 1 byte that contains the length of the content we want to encode. We'll have to split that byte into 2 parts so we can append it to the data stream, which leaves us with 1.5 bytes of data in the stream. Now we append the actual content. So we'll have to split all of the ASCII bytes and append them. As mentioned earlier, each version can cover a certain amount of data, and as the length of our input will hardly ever exactly match that amount, we'll fill the rest of the available content size with hex values EF and 11. This was step number 2, and while this is only iterating over less than 100 bytes, there are a lot of division and multiplications involved in loops, which is a real challenge for the BASIC interpreter. So it still takes about 3 to 4 seconds on the C128. Step number 3 will be to add the error correction bytes to the data stream. For version 5 codes, for example, 26 error correction bytes are calculated. The number of bytes for the different versions can be taken from a table. The error correction method used is Reed-Solomon forward error correction. And for this part, I just followed the existing Java implementation as I don't really understand what's going on. So we need to compute an array of reminders, and the input for that is the data stream so far, and an array of polynomials. And these arrays are multiplied over and over again, and the results are exclusively ORed with the result of previous iterations. The comment in the Java code base says this could also be a lookup table of 256 by 256 entries, but that would be 64 kilobytes in size, and that's all the memory we have, more or less. So we will stick to calculating these. The operations involved are pretty simple by themselves: bit shifting, exclusively ORing, and multiplying. But it's the number of iterations that really add up. Once we're done with this, we append the ECC bytes to the data stream and end up with a total size of 134 bytes. In Commodore BASIC at 2 MHz, this step takes 1354 seconds, which is about 22 minutes. Well, needless to say, this already spoils the fact that a QR code generator in Commodore BASIC is not something that's usable in real-life scenarios. But it makes it even more interesting to see how C and assembly language implementations perform. Now we're ready for step 4, aligning the data inside the matrix. No, wait, before we do that, we will need to write the static patterns that are so characteristic for QR codes. We need to write these now, so the actual data stream later can skip the according fields. We do not want to overwrite any data after all. We start with writing the timing patterns. QR code readers look these up to know how wide and tall one module in each row and column is. This way, rectangular codes work just as well as square ones. Then we have boxes on 3 corners, another box close to the bottom right corner. And also, we are writing this one module. This defines what a logical 1 looks like. In this case, it's a dark module. Now, when we write the data modules in the next steps, how do we know that a field in the matrix is already filled with a module that's not supposed to be overwritten? The solution is we don't just use a full byte for storing light or dark information, we also use the other bits of the byte. So a value of 128, that's the highest bit set, means this module is ready to be used for data. So we initialize the matrix with values 128, and when we write the alignment and timing patterns, we write the value 0 or 1. The highest bit is automatically cleared. This step looks pretty simple, still it takes about 9 seconds in my implementation at 2 MHz. And now we're ready for aligning the data inside the matrix. For this, we'll write the bits of the data stream as modules. The bits are laid out in a zigzag pattern, which is very well visualized on Neyuki.io. How do we deal with occupied modules? Instead of writing the value, we'll just keep moving until we hit the next free spot. We can do that by checking the highest bit. Also, we'll check boundaries by comparing our current position with the lowest and highest memory addresses of the matrix. If we hit the boundary, we know that we have to change directions. And this works pretty well. Now, we're not just writing values 0 or 1 here. We're writing 64 or 65. Still 1 and 0 in the lowest bit, but with bit 6 always set. Why? Because QR codes are exclusively ORed with 1 out of 8 bit masks. This is to make sure that the encoded data is not easily recognizable, that no recurring patterns are visible, and that no patterns appear that could be misinterpreted by readers as alignment or timing patterns. The catch is that not all modules are exclusively ORed, only the data modules are. So, when we apply the masks later, we can evaluate bit 6 to know whether a module is to be exclusively ORed or not. This step takes about 60 seconds on the C128. The final step is to create the XOR masks and to apply them. These are the 8 masks involved. For simplicity purposes, I just calculated 4 out of 8. By the way, where do we store the masks? We'll just use the matrix itself. We used bits 7 and 6 to identify if a module can contain content data and if it is to be exclusively ORed with the mask. And we used the lowest bit to specify the actual content data value of a module. So we still have 5 bits left, and we'll use 4 of these to store the masks and the mask error correction format patterns. And we need another piece of information. The QR code reader must know which one of the masks we applied and also which level of error correction we are using. This information is encoded alongside the alignment patterns in the 3 corners. These 15 modules contain 2 modules for the error correction, 3 modules for the mask, and the remaining 8 modules are again Reed-Solomon calculated error correction modules. As we only use low error correction and 4 possible masks, we can just use 4 pre-calculated values depending on the mask chosen. The regions where these 15 modules are written to are not to be exclusively ORed with the mask, and they are not to be occupied by content modules. So we'll just store them in the same bit as the values of the according mask. And that's it for the last step. BASIC takes about 95 seconds at 2 MHz for doing this in a 37 by 37 matrix. Before we talk about displaying the QR code, I'll present you with the total time required for this generation process. It takes about 1526 seconds on a 2 MHz C128, which is about 26 minutes. On a 1 MHz C64, this took 2667 seconds, which is about 45 minutes. I also compiled this with reblitz 64. It took 512 seconds, that's about 8.5 minutes. This matches my previous experience with the Blitz Basic compiler. You can find more information on that in a previous video. Also, I'll link to 1570's browser implementation of the reblitz 64 compiler in the description below. And I used my Ultimate 64 at 48 MHz to run the interpreted version. It took 57 seconds. And the reblitz 64 version on the 48 MHz Ultimate still took 10.7 seconds. No blitz optimizations for variables or loops have been made to the code, so there's also a lot of room for improvement here. The Ultimate 64's 48 MHz are close to the Mega 65's 40 MHz. Have you ever wondered if the Basic 65 interpreter itself is faster than the V2 or the V7 interpreters? Let's just watch in real time how long that takes. On the Mega 65 in Basic 65, it took close to 24 seconds at 40 MHz compared to 57 seconds on the Ultimate's 48 MHz. If you're interested in the details of these versions, feel free to follow the link to my GitHub repo. And I also converted the code to the X16, and there it took 329 seconds, which is about 5.5 minutes. So just like the C64, the X16 also performs a bit better per megahertz than the C128's basic interpreter. I didn't have any basic compilers available to try on the X16 or the Mega 65, unfortunately, so that's all I can show so far. Oh, I almost forgot. Here's the proof that the basic QR encoder actually works. The basic implementations take about 9 kilobytes of disk space and RAM, and they take up less than 1 kilobyte for basic variables because they heavily rely on peek and poke. Now, what about C language performance? I didn't build a C implementation myself, but I found one on CSDB. That binary is about 20 kilobytes in size, and this takes about 1 minute on a C64 to complete. But to be fair, that C implementation is a full implementation that didn't take any shortcuts, just as I did. The source code comes inside of the zip file of the download, so feel free to investigate and share your thoughts. Still, the runtime is an issue. And also, it just prints each module as a space or inverted space character with a maximum of 25 lines available on the screen. This equals version 2 codes, which limits the content length to 34 characters. Before I share the runtime results of the assembly language version I built, I would like to explain how I implemented visualization to easily fit 37 modules to screens with 25 lines. Petsky characters themselves hold the solution. Several characters allowed to have 4 modules displayed in a single Petsky character. When we parse over the result data of our calculations, we just don't go line by line. We always take 2 values of the current line and the 2 values right below. The values of the 4 modules are bit shifted in always the same order. Module on top left is taken as is. The module to the right is shifted to bit 1. The left module on the second line is shifted to bit 2, and the fourth module is shifted to bit 3. In essence, value 2 is multiplied by 2, value 3 is multiplied by 4, value 4 is multiplied by 8, and these values are added up. This results in a maximum value of 15. Now, all we need to do is to create a lookup table that contains the screen code or Petsky code of the characters in question, and we're good. Some of the characters are in the Petsky tables just as we need them, and some of them just need to be inverted to show the right combination of modules. As you can see, this works pretty well. And to the right you can see a code that had a bug in the rendering routine. Only the rightmost column is affected, but due to error correction it still works. Now finally, let's look at the raw power of 6502 assembly language. The program I show you now is a basic program, but for the actual QR code generation, it's calling a machine language binary. This is what's loaded right after the program is started. It immediately starts with rendering the link to the GitHub repo of this, and it takes 94 jiffys at 1 MHz for a version 3 QR code. That's 1.5 seconds, isn't that amazing? At 2 MHz, this would be about 40 to 50 jiffys, which is even less than a second. Now I'll demonstrate different bit masks. I'll use the URL of the Forum64 for that. That's version 2 code, and that only takes 50 jiffys. Yeah, let's test if this works. And now keep an eye on the QR code structure. Now this is rendering with bitmask 2 and bitmask 3. And let's open that again on the mobile. And it shows the same page as before, although the code looks different. How large is the generator binary? It takes up about 9 blocks. That's just a little bit over 2 kilobytes, and the memory required for calculations is about 1.5 kilobyte. That would make 3.5 kilobyte of total required RAM. Could we maybe even squeeze that into the memory of an unexpanded VIC-20? Before we check that, if we just want to show static QR codes in our programs, do we still need the full encoder? No. So I tried to see how much memory it would take to store the full QR code matrix itself, where each module is really just stored as a bit, not a full byte. For a 37 by 37 code, this would be 1369 bits, which is roughly 172 bytes. We can just store the index values we calculated. Then we would still need the program code that renders the QR code to the screen. I was able to squeeze this into 99 bytes. So I added a function to the generator that allows you to write this to disk. You need to provide the address the machine language program is going to be executed at and a file name. Now the static runtime code is written to disk. And now the data of the current QR code. We defined address 49152. This is a common memory area for machine language programs on the C64. So we generate this on the C128, but we are going to use it on the C64. Here's the directory, and the runtime file is only one block. We'll just load this with "8,1". Then we'll need to poke screen width into the accumulator and screen memory start address in the X and Y registers, which is done through addresses 780 through 782. Et voila, the QR code on screen just within 2 jiffies. And depending on the size, it takes less than 256 bytes of memory. So you can fit a full QR code with rendering code into one single page of a GeoRAM expansion, for example, or the tape buffer if that's your thing. So it should be really easy for you to bring this into your programs if you want to. This also works on the VIC-20, of course. I have prepared a small basic program which loads the one block machine language runtime. It loads that, sets the colors, and then also pokes to accumulator X and Y registers. Sys 7097 executes the runtime, and I just made a rough guess about which address would be unoccupied. When we run this, one block is loaded really fast and the QR code is on screen. This version had still a bug, by the way, as you can see on the bottom right side of the code. Now, what if we want to have QR codes in our picture editing or desktop publishing programs on the C64? Isn't the text screen output a bit unpractical to reuse? I, for example, use Godot a lot, and in the past, I would generate the QR code on the PC, save it as a PCX or GIF file, put it onto an SD card, load it into Godot, and save it in a format that's supported by whatever program I'm working with, Printfox in my case. When I had the QR code generator implemented, I got in touch with Arndt, who is still maintaining Godot to this day, and asked whether he'd be interested in wrapping this into a Godot module. And he did. He was just as excited as I was about this, took my QR code generator code and did what was needed to forge it into a Godot expansion module. You can find the download link in the description. Going forward, I just can generate the QR codes directly on the C64 and save it in Printfox format. Okay, now with all that, there's really only one last thing left to find out. Can an unexpanded VIC-20 with just 3.5 kilobytes of free RAM generate QR codes? To find that out, I created a dedicated all-in-one VIC-20 version of the binary, including basic wrapper code. And yes, it does. I stripped it of the runtime generator and there's only one bit mask to use, but still, it proves that the VIC-20 can do this in about 1 second. The GitHub link works. Let's check another URL, the VIC-20 denial forums. And it also works. We made it. This video is the result of about 6 weeks of programming just for the generator and 2 or 3 weeks more for the runtime and the showcases. If you didn't yet, please make sure to like and subscribe, and I'd love to hear from you if you can use any of this for your projects. Thanks for watching until the end. Maybe check my other videos and feel free to leave a comment. See you next time here at the 8-Bit Theory.